So let us look at the abstraction that we are going to use in this particular course. What we are saying is the instruction memory, right, read is what is highlighted there, and the gray shade basically says that it is occupied for the full cycle. Instruction memory is occupied for the full cycle. So now you are doing register read, okay, and therefore that is happening on the rising edge on the first half of the cycle, right, and the ALU operation again is happening after that, right, the execute stage, and that is going to basically be ALU is going to be busy for the entire clock cycle, okay. Then you have the data memory read or write that is needed, okay, and then you are going into the register file write back, okay. Again you see that the RF portions alone are shaded differently for read and write. So the register write back is shaded in the first half, whereas register read is shaded in the second half. There is a reason for that. I will come to this in some time, right. So let me now again make a copy of this so that I can explain this in some detail out here, okay. So let me come back here, okay. So I have a nice representation of our pipelined processor execution. So what we are doing now is we have considered a very interesting sequence of instructions, a very simple sequence of instructions, which is load word, okay. Instruction, this is instruction 1, 2, 3, 4, 5 and 6, right. So if you look at this, the first instruction obviously will take 5 cycles, but the second instruction will be done in the 6th cycle, 7, 8, 9, 10. So in 10 clock cycles you are done with all 6 instructions here, right. So what is actually happening, you are doing a load word, okay, S2 comma 40 of S0. That means what is being done, right, you look at here, after the instruction memory IM block, what you get is the instruction has been, the instruction has been obtained from the memory and you have given it to this flip-flop. In the next clock cycle that will go in. Actually you do not know that is the load word, but you have fetched that machine code. The CPU will know it's a load word only after you go to decode, right. But you have, what this LW is saying is, you have fetched the machine code corresponding to this load word instruction that is available here, right. That's what has come out. Now what you have done is, you have done the register file decode in the next clock cycle. RF decode is telling you what the read registers are, and also the control block has finished decoding signals, right. In this case it's an immediate type of instruction, so you are going to do S0 plus 40, right. So therefore you see that it has pulled out S0 register which is from here, right, and then it has pulled out 40 which is the immediate argument, and that is being, it is going to be given to a flip-flop, and in the next clock cycle that will be latched on, right. So it is T setup ready before the flip-flop, next clock cycle it gets latched on and given to the ALU for consumption, right. So when you are done with this stage, you basically will get this S0 plus 40 here, that result will be available, okay, and then you give it to another flip-flop, next clock cycle, the 4th clock cycle, that is going to be given to the address of the data memory. The control signal has also got to fire correctly, so that you read in that clock cycle and all that stuff. You read it, you get the data out of the data memory, and then after that you have already obtained this S2 here, because that's the register file write back that you are going to do into. The data has come out of S0 plus 40, that address. You got 32 bits out of that address, and you are now ready to write that back into the register file, and that's what is happening in the clock cycle number 5, okay. So now what is happening, the next instruction, right, which is add S3, S9, S10 has already been fetched. So in clock cycle 2, while the register file decoding and all was happening, right, the register decoding was happening for instruction 1, the processor has already gone and fetched the instruction 2, and therefore you have basically got add here already corresponding to this. Okay. Then you go in there, and now what you are doing, you are trying to add S9 and S10. Okay, and therefore the two arguments are basically after the register decode, you get these two corresponding to these two things, and then you are performing the addition using the ALU. Okay, you are performing the addition using the ALU, and here you will get the result of S9 plus S10 register. Whatever that result is, you will get it here. Okay, and then now the next pipeline stage is actually supposed to be data memory read. Okay. In a multi-cycle implementation, it was possible for our type of instructions to just go through this fetch, decode, execute, then write back. Now, if you had a load instruction, you would do the data memory read. You would use that extra clock cycle. That's why something would take 2 clock cycles, next thing would take 3 clock cycles and all that, and we were able to optimize the time. On the other hand, in a pipelined instruction, in a pipelined implementation, you cannot neglect that clock cycle. It has to go through, because otherwise while something is fetching, the other is decoding and all that, right? So therefore you cannot skip this cycle, right, and just say that okay, in clock cycle number 5 I will just do register file write back of my instruction 2. Why? Because register file write back is already happening for the previous instruction, instruction 1. The register file write back stage is busy with the register that instruction, and therefore if you want to schedule this correctly, you have to wait for one empty clock cycle, and that's why this particular DM is not shaded in gray. You just leave it empty, okay, to indicate that this cycle is an empty waiting stage. Okay, it's a waste, but you cannot help it, and you are doing nothing in the data memory in this particular cycle. Okay, so the key point is, for this particular instruction, the only stage in the pipeline that is free to do something is this data memory stage. Everything else is busy with something else, right? For example, the ALU register file decode is busy, right? I'm sorry, if you look at it in that cycle, the ALU will be busy with the next instruction's execution. Previous instruction register file write back is happening. So the only block in that pipeline that is free to do something is the data memory, and that's why that part you either have to be idle or you have to use that block to do that in part of the instruction. Otherwise nothing can be done, right? Finally, there's nothing to be done in data memory read, so you just leave it idle, and then you basically have decoded this S3, and that is the result of S9 plus S10 is now ready to be written back into the register file appropriately. Okay. So likewise, the third instruction is doing S4 T1 S8. Okay, subtract S4 T1 S8. So that's why in the third cycle you are fetching this instruction corresponding to this particular opcode, mnemonic, right, and then you are giving these two operands again to the register file here, right, and then you are doing the subtract operation, right. So you see inside the ALU you are indicating whether you are doing plus, minus, whatever ALU operation you chose, that is as per the instruction, right, and then you are doing therefore out here you will get T1 minus S8, right, and then you are obviously because this is an R type of instruction, you are going to skip the data memory phase part again here, and you will come back to register write back into S4, right. So that is what you see here, S4, right. You are able to write back into the register file at this stage, right. Now again you have an AND of S5, S11, T0, okay. So the fourth instruction, therefore the fetch will happen in the fourth cycle, right. And you are going to get the AND out of that, okay. The arguments to the ALU will be S11 and T0, that is as per here. You are getting the AND operation here. Remember, you are indicating what operation to be performed in the ALU. Then again you have to skip the data memory part here because there is nothing, it is an R type instruction, and finally you get S5, okay, back here. So if you look at the instruction 2, 3 and 4, they are all R type instructions, so they will be very similar in their execution flow. The only thing that changes is basically the operation to the ALU and the input registers which are going as operands to the ALU, right. Now the fifth instruction is a store word, right. What is a store word? You are basically doing this T4 plus 20, and you are going to take the contents of S6 and give it to T4 plus 20, okay. So therefore you have fetched the instruction as per corresponding to the store word, and then remember you are now doing T4 plus 20. So T4 has to go here, okay, corresponding to this, and 20. So don't come and put this here, that is not correct, because that is the that is the register whose value is going to get written into the memory. That is what store word means. Store word means you are saying that I will write the contents of T4 plus 20 with S6, okay. So ideally the mnemonic should have been other way around. If you had done T4 plus 20, T4 20 there, then it might have been easy for you to realize that okay, T4 is going to this first argument of the ALU, source A, and 20 is going to source B, and the second register is basically whose value is going to go and get written into the memory, which is basically the S6, right. So anyway, so after that what you are going to basically do, right, is you are going to write the contents of S6 into the, so here you evaluate T4 plus 20, okay, and then you are now going to write the value of S6, okay, into the data memory. So you are going to feed this T4 plus 20 as address, the data 32 bits will come from S6, and then you will assert the write enable, and the write would have happened in this stage. Now you note that because it is a store word instruction, once you write something back to the memory, there is nothing else to be done, the instruction is over, and that is why this last stage is going to remain unused. The RF register file write back is blank in this particular instruction, okay. So after that what we have is, we have used the S7, T2 and T3, okay. So this is another last instruction which is again a logical instruction here, which is again R type. So it should be very similar in the flow to instructions 2, 3 and 4, right. Then you are getting T2 and T3 out here, right. You are going to evaluate T2 or T3, right. And of course there is no data memory read to be read, data to be read out from the data memory, or you are not writing back, so the DM is left empty, you are not shading that, and then you are going to writing the result of T2 or T3, bitwise T2 or T3 into the S7 register. So therefore finally you are coming back here, okay. So this is a very nice sequence of instructions that we have had, okay, where we have been able to execute a certain sequence of instructions in this pipelined implementation. Okay. So now what we find is, this is very good. This seems like unbelievable to be true, right? So there has to be a catch somewhere. So what is the catch? The catch is that we did not worry about any sort of problem in the sequence of instructions. Okay. So the sequence of instructions here, for example, S0, right? S2 is a destination register here. So if you look at this, just look at the destination register S2, then S3, right? So the source registers for subsequent operations were not the destination registers in any previous operation. Okay, in the first instruction you wrote to S2, second to S3, third to S4, right? And therefore the source operands really came from, you know, some other operation, right? So now for example, let us say that if I add a 7th instruction here, okay, which was basically I will say add, okay, S6 comma S2 S4, okay. So what you see is, by the time you have come to the clock cycle 10, right, all S2, S4, S6, all these registers have been written back, you know, by their respective operands correctly, and therefore if I go ahead and do another fetch, decode, execute data memory register file here, things will happen perfectly without any problem, right? So the trick really is in the choice of the instructions that we have, you know, made here, and that is why the whole thing is working in a very nice and beautiful manner. Okay.